Welcome to presentation 18. Today we're going to be talking about the joystick. Joystick belongs to our layer 3 architecture. This is shown in yellow. In addition, I've put in a marker under 3 items of our architecture. One in layer 3, which is the servo motor, and 2 of layer 2, which are AD framework and time counter framework. Now these 3 items that have the markers, you should review my presentation, which is going to make it much easier to understand the joystick presentation. So today's agenda, I'm going to be talking about joystick functionality and followed by a sample program. So let's get going. Joystick functionality. A joystick is an input device that converts physical movement into voltage. It consists of a stick that pivots on the base, enabling movement in various directions, such as left to right and up to down. Programming a joystick typically involves reading the analog signal generated by the joystick and converting them into digital values, processing these digital signals to determine the exact position of the joystick, taking corresponding action, such as moving an object, controlling a servo motor based on the joystick position. So here I show you a typical joystick. So this is left, center, and right. When this moves, it's going to generate a voltage. We convert that voltage from analog to digital and then decide what's the position of the joystick and take according action. So let's look at a little bit more details. So typically, when a joystick all the way to the left, it's going to output 0 volts. If the joystick is in the center position, it's going to output 2.5 volts. And finally, if the joystick is all the way to the right, then it's going to output 5 volts. So let's see what would be the conversion from analog to digital for a 10-bit resolution. So we would say all the way front, that would be 0 volts, and that would be digital 0. The joystick on the center, which would be, like we noted, 2.5 volts, the digital value would be 512. Next, if we push it all the way down, then we would get a 5 volt output from the joystick to a controller, and that would convert it to a 1023 value. Always talking about 10-bit resolution. If you have 8-bit resolution, those numbers would be differently, of course. Now if we move to the right, that would have 0 volts, and the digital would be 0. If we move it to the left, then we would have 5 volts, and the digital value would be 1023, and the center, of course, would be the same, which is 512 approximately. So let's look at our program. So what we're going to do is we're going to take a joystick and we're going to connect it to PC1 and PC2, which is ADC1 and ADC2. So the idea is that you move the joystick and you have an input to ADC1 or ADC2, depending whether you are on the X or Y axis. And according to those values, you are going to drive two servos, servo 2 and servo 1, which are going to be connected to PB1 and PB2. So the idea is when I get the servo to 0 degrees on PC1, for example, then one of these servo would go to 0 degrees. So let's look at the statement of the program. Read analog input from the joystick, that be ADC1, ADC2. Convert analog to digital using a 10-bit resolution. Next, drive the servo motor as follows. Rotate shaft to 0 and 180 degrees based on the input voltage between 0 and 5. You're going to get in ADC1 or ADC2 values between 0 and 5 volts, and according to those values, you're going to drive your servo motor between 0 and 180. 0 volts corresponds to 0 degrees, so you get 0 volts, you're all the way to the right. 5 volts, you're 180 degrees. So as you move your joystick back and forth, you should see your servo motor move from 0 to 180, depending in what axis you're moving your joystick. And finally, all software required to configure the servo is going to be included in the framework _servo.h. Basically, all I'm saying is that the main is going to cover the getting the inputs from the joystick, converting it to analog to digital, and moving the servos. The initializing of the servo and making this happen with the pulse width modulation is going to be included on the framework servo.h. So let's look at the program. Sorry, before we do that, let's look at some calculation. So what I did is I decided to do some calculation so it's going to be easier to understand the program. So the ADC circuit requires an input clock frequency between 50 and 200 kilohertz. That comes from the data sheet, and I had explained it before when I talked about the ADC, or in the ADC presentation, I should say. So we have a formula which says that the input clock to the ADC is equal to the microprogrammer clock frequency divided by the prescaler. Now, what we need to input into the register is the prescaler. So the prescaler is going to be equal to the clock frequency divided by the input clock to the ADC. So let's assume that the input is 50 kilohertz. In that case, the prescaler would be 320. Next, let's assume that the input is 200 kilohertz. In that case, the prescaler is going to be 80. So now, for our frequency to be between 50 kilohertz and 200 kilohertz, then the prescaler has to be between 320 and 80. Now the prescalers available are 2, 4, 8, 16, 32, and 128. The only prescaler that is between 320 and 80 is 128, so that's the prescaler that we have to use for the analog to digital conversion. So we need to use the 128. Okay, let's go to another calculation that this has to do with converting volts to shaft rotation, to servo motor shaft rotation. So how do we figure out we can evolve how far do we need to move our shaft. So let's look at the servo motor parameters. So we know that a pulse which is high in duration of 5 milliseconds is equal to 1000 ticks, and that corresponds to the 0-degree rotation. And by the way, we looked at these items and it was explained during the servo motor presentation. So this is kind of a refresher. Now, for 200 milliseconds, which is 5000 ticks, the servo motor moves to 180-degree rotation. So if I put a pulse width modulation at 25 hertz, 20 milliseconds duration, and it's 1000 ticks high, then the servo motor to 0 degrees. If it's 5000 ticks, then the motor moves to 180-degree rotation. So now let's look at the joystick. Down position, 0 volts is going to be 0 digital conversion. Next, 5 volts, which is the up position, digital conversion with the 10-bit is going to be 1024. So now let's do the conversion from volts to ticks. Okay, so number of ticks. So we have 5000 ticks, which is the maximum 180 degrees. We divide it by 1024, and that gives us the number of ticks per volts. Next, we multiply it by the number of volts that we are reading. Now, the servo motor 0 position is at 1000 ticks. So this number plus 1000 is going to give us the actual position that the servo has to go for the applicable or for the voltage we just read. So going through this operation, the number of ticks of rotation is going to be the conversion results times 4 plus 1000. Now don't forget, this is for the 16-bit resolution. If we do an 8-bit resolution, then this 1024 number has to change. So with this information now, let's go to our sample program. I will start by giving you a global view of the program. So let's start at the header. The header, I've included a include file called framework_servo, which is going to be responsible for initializing the pulse width modulation signal required to drive servo motor 1 and servo motor 2. Next, we have the init ADC. This routine will initialize everything required to get the analog to digital conversion. Next, we have two routines, enable ADC1 and enable ADC2. What they're going to do is they're going to read the analog signal from the ADC1 and ADC2 ports connected to the joystick, and it's going to digitize that information. Next, we have process x-axis and process y-axis. What these two routines do is they get the digital information obtained from the joystick and converts them to rotation and drive the servo motor 1 and servo motor 2. And finally, we have the main, which what it does is initialize whatever needs to be initialized and then calls out the X and Y axis routines to drive the servo motor shaft position. So let's look at the details. So you need the ADC. So the first thing it does is disable the digital inputs that are for ADC1 and ADC2. Next, it calculates the scalars needed to drive the ADC, which I already explained that calculation. And finally, it sets the registers so that the voltage reference is going to be the ABCC, the input voltage to the controller, microcontroller. And again, all that was explained in the analog digital presentation, so I'm going a little bit fast through these sections. Now let's look at enable ADC1. So like I noted, this is going to get the information from the joystick for the ADC1 joysticks. So I would be PC1, and it's going to, the analog information is going to be digitized, and it's going to be returned as a output to this routine. So what do we do? So the first thing, we need to select the input channel, ADC1, which is this one here. Next, we give the command to start the conversion. That means to read the input from the joystick. Then we have a while. That's where we wait for the conversion to happen. Next, we get the results, which is contained in two registers. We put the information together here by shifting the conversion result high to the left 8 position and using the conversion result as is. That's basically, we have the 10-bit resolution. And finally, we return the conversion result. Now, let's look at the enable ADC2. Again, it puts out the digital conversion for the ADC2 input from the joystick. So ADC1, we could say the X-axis inputs, and the ADC2 is the Y. We could say up and down, left to right. So it's going to be same as the enable ADC1, except that we select the ADC2 as an input. So we select this one, and then we perform the same conversion. We start the conversion. We wait till it's concluded by looking at the flag. Next, we put the result into the conversion result, and we return that value. Next, we have the process X-axis. Now, these items up here, I already explained how we get to this equation, to the rotation equation. So what this process X-axis is doing is calls the enable ADC1, get me the digitized value of the ADC1. So get me a digital value that represents the location of the joystick, multiplied by 4 and add 1000. That's going to give me the number of ticks for the signal to be high. And then I go ahead and put it on the OCR1A register. Now, the initializing of this register, I'm going to show it on the include file, but it's very similar to what we did on my presentation dealing with servo motor. So we We get the digital value of the location of the joystick. We multiply it by 4 and add 1000, and that gives me the number of ticks, which represent for the pulse width modulation, how long it's going to be high. And I put it on this OCR1 register. Next we have the Y register, which is going to be same as the X, except that we use enable the ADC2. So this routine is getting the digital value of the ADC2, and it converts it into ticks, which are going to drive the servo motor. So now let's look at the init, at the main program, I should say. So we have the init pulse width modulation, init ADC. Now we already looked at the init ADC. However, the init PWM is going to be in the include files, which I'll explain in a little while. So let's look at the main program. So we initialize pulse width modulation, we initialize the ADC, and then we get into our while loop. So what the while loop does is as follows. It gets the joystick x-axis, the ADC1, and then it places the servo motor in the correct position according to the input from the enable ADC1. Next, we have the process the y-axis, which places again the servo motor on the correct position. Wait 50 milliseconds, and then we do that forever. So we are monitoring the position of the joystick, and according to the position of the joysticks, we're driving the servo motor. Okay, so now let's look at the include file. So let me go back so you see what I'm talking about. So I'm talking about this framework servo include file. Now the reason we know we're using that include file, because that's where the init underscore PWM routine is defined. So this is the framework servo, which I call framework. I've called the framework servo, which is an include file that takes care of initializing the pulse width modulation, which is going to drive these two servos. So the first thing we do is we enable the pin B2 and pin B1 to output. That would be these two signals. Next, we set those pins for fast pulse width that gets set to high on compare match, and it gets clear at bottom. Now I've explained that during the presentation on servo motors. Next, I set the waveform to the fast mode with the 16-bit resolution. And finally, what I'm doing here is setting the output period to 20 milliseconds, 20 milliseconds. And that's what these three parameters do, which sets the ICR1 to 39,999. That's the number of ticks for the clock to reset. So anyhow, I've explained this program that basically gets input from the joystick in two analog channels, ADC1 and ADC2, and drives two servo motors connected to PB1 and PB2 to the correct position based on the joystick. Now, most of these items have already been explained in other presentations, so all I'm doing here basically is putting together what I've already presented before, incorporating a joystick. So let's continue with the presentation. Okay, with respect to this program, I would encourage you to look at my presentations before, if you have any something that you don't understand here, because everything was explained in those presentations, and this is basically putting everything together which we have learned so far. So this gets us to the summary. Today I talked about joysticks, gave you a good idea of how they function, definitions, and then we went through a sample program. Well, I hope you've enjoyed these presentations, and thank you very much.